Hello everyone, welcome to my video. So in this video, I'm gonna talk about how to derive from the f decomposition. That's it, f equal to fe times fp, where f is the deformation gradient tensor, to get our additive decomposition in terms of d, where d is the root of deformation tensor. The second bar. The two bars denote that d and f are second order tensors. So first, let's recall that the deformation gradient tensor f is defined as this, where this lower case of h denote the position in terms of current configuration, and this upper case of h, it denotes that the location is in terms of reference configuration. So let's start our derivation. First, we all know that the deformation gradient tensor can be decomposed as I just wrote, the multiplication between elastic part of deformation gradient tensor and the plastic part of deformation gradient tensor. And also there's another relation we all know, that is the velocity gradient L can be written as this. Here the dot denotes the time derivative, and this -1 denote the inverse. Okay, some further background knowledge is that, remember that the velocity gradient tensor L is defined as we should have this because x are all vectors. So here, and u is the displacement, which is denoted as this. Here, the velocity gradient tensor is defined as the derivative of displacement at current configuration in terms of the vector at current configuration. Right. So here, based on this, so we number these equations 1 and 2. So if we substitute equation 2 into 1, that we get, if we substitute equation 1 to equation 2, that's what we can get. What we can get is Fe, Fp, I will do a quick one because I already did all of this. So this dot is for this whole product, and we substitute that. So remember that E dot Fp, let's see, it's like this. So this is a simple one. So we do this. So what we get is this plus, I will do a very quick one to save both your and my time. Here we have Fp inverse, Fe inverse. That's a simple one. And we can further get plus this. So now we can see that this can be cancelled out, which equal to 1. And further, we get further, so we can write this as this. where we define this elastic part of the velocity gradient tensor as this. You see, compared with this equation with equation 2, that they are essentially the same thing. And here we also write LP this as LP. So if we do this, we can simplify this relation to get we get this LE plus FE times LP times FE inverse, right? And then we name them as equation 3. So far so good. Oh, just let me know if you have any questions. Just leave it in the comment and I will address it later. So the goal of my video is to let you guys understand how to derive these fundamental equations, which will be very useful for your future career in solid mechanics. And here, one important assumption appears is that we assume the elastic string is small, or it's infinitesimal compared with its unity. So we will just simply write as small elastic string assumption. So based on this, that we can write following. Okay, so another thing to recall is that, remember, we have polar decomposition, and here we use left polar decomposition for FE, elastic part of deformation gradient tensor. We write them as the so here is E and RE. And also, because of this polar decomposition, that we have this orthogonal, and this is a symmetric tensor. And further, if we and also remember that R represent the rotation and V represent the stretch, and that's also the reason why R is not symmetric, because R is orthogonal. So we have, remember, from our fundamental class, we know this. And here we can further write this stretch as this VE as a unity tensor plus the string part as this. So because of our small elastic string assumption that we have theta, the absolute value of theta is far less than 1, and because of VE is symmetric, so we have AE is symmetric as well. Is symmetric. Okay. So based on this, so basically is that what we need to do is substitute this equation 4 into equation 3 to simplify. I mean, actually, to be honest, it's not simplified, but to make it more complicated, or to make equation 3 more complicated. But let's do it to see what we can get. So due to the time, I may not do the whole process here, but if you really follow this, you substitute, let me use another color, you substitute this FE into, you substitute this whole part into here, which is here, and also here and here. What you will get is this. So substitute equation for the equation 3, we have, what we have is L equal to LE plus this stretch part times rotation, and I did this in my spare time, but just due to the time limit of this video, I do not want to make it super long. So we have this here. Oh, remember that. Okay. I did not substitute into LE, but okay. But you can do it, but even though it's not necessary. So here is that we have this, and if we read them out, that we can have LE plus RE LP RE inverse plus theta A RE LP RE. This one. First I do this part, and second I do this part. And further not plus, it should be a minus, because we should have this as our third part. Third part and fourth part. You know what I'm saying? And third part, it should be minus RE LP RE inverse theta A. And finally we have the, oh no, sorry, here's not 5 part, here should be the fourth part. What I'm doing, okay. So it should be the fourth part, and we get theta A E L P R E inverse and A. So this is what we get. And here, let's use our assumption. Is that because our assumption is elastic string is small, so what we have is here that this is further less than 1, and also, I mean, because of this, so we get this is about 2 1, and here, so what we get is we get this part, and we name this part as equation, let's see, equation 5 within the green bracket. So now what we would like to do is we would like to recognize which part within this equation 5 belongs to elastic and which of these belongs to plastic. And also further, which is symmetric and which part is antisymmetric. So we can write out this. Remember that we have this decomposition where D is the rate of deformation tensor, is symmetric part, and W is the antisymmetric part. Because we have, read them out, we have this is the symmetric part, this is the antisymmetric part. So what we want to do here is to recognize which of these green bracket in equation 5 is symmetric part and which of them is antisymmetric part. So we can recognize which is D, which is W, and further we can write out the additive decomposition in additive decomposition in terms of D, remember? So here, let's see. So just as what we write for our L, so for LE and LP, we can also write similar things. So for LE, we have D plus WE, and for LP, we have DP plus WP here. And we name this as thirds. So if we substitute equation thirds, into equation 5, we get a long equation. So if we substitute, we can get, I will just directly write them out, D plus WE here LE equal D plus WE, and so for LE we have this part, and for this part we can write them as RE dP plus WP times RE inverse. And the third one is this one. Let's write this out. It equals to so the third one is theta 8 RE LP equal to dP plus WP RE inverse. This inverse. And lastly, it's fourth part. We write them as, oh no, plus, it's minus. So it's minus theta. Oh, we just write this theta in ahead here, because it's not a matrix. It's just a scalar. So we have this LP RE inverse A. And because of this, now we have this term. This is equation 5. After we substitute the equation 6, we get this equation 7. We name this as equation 7. And now let's pay attention to this. So which part of this belongs to the antisymmetric part, and which of this belong to, the symmetric part and antisymmetric part? So as we see here, this must be symmetric part, ds, right? This one, of course. And this is antisymmetric part. This is symmetric part. This is antisymmetric part. But for this term and this term, it's a little tricky. So I will just tell you directly is that W part is symmetric part. Oh, here. Oh, what did I do here? This should be read out as dP plus WP, sorry. And W is symmetric part, and D is antisymmetric part. So I will just right quick to show you this. Is that because it's tedious to see that it's because A RE D P plus WP RE inverse. This is this part. So if I do a transpose of this, what I get is that. Oh, also another thing to see is that because this R matrix is orthogonal, so we have R inverse equal to R transpose. So here we should get, what we get is R E right. RE and dp transpose of it, dp and wp, because wp is antisymmetric. Here we have the E transpose and times A, because transpose of A equal to A. A is a symmetric matrix. And for this part, we get theta RE dp wp RE inverse A. And the transpose of this equal to theta. Oh, remember that we have theta here, right? It's equal to A times E, right? The transpose of this equal to itself. I mean, equal to inverse of transpose. And here we have dp plus wp, now plus minus re transpose, right? And if we have detailed observation, we can find that because here is a minus sign, so if I add this minus sign here, minus sign here, so we have, so one tricky thing that A is at different position. So this make, if you make comparison, you can see that the whole equation of this, if we write this in terms of, I mean, because we have two terms here, because we have two terms here, we have two terms that, and if we, and this part equal to this part, and this part, you see, because here are two minus signs, so we get positive sign, equal to this part. Because of this, so now we can recognize that the term involved with WP is symmetric part, and term with WP is symmetric part, but the term with DP is antisymmetric part. So all of this, so with all of this, our goal is that, okay, so let's write out equation 7 again to have a detailed discussion. Is that we have DE plus WE and RE dP plus WP RE transpose plus theta A RE dP plus WP RE transpose minus theta RE dP plus WP RE transpose A. And because of this, so now because we know that this is symmetric part, symmetric part, symmetric part, symmetric part, so we only pick up the symmetric part. What we get is that because L equal to WD, remember this decomposition, so we write all the symmetric part as D. So what we get is D equal to DE plus RE dP RE transpose plus theta A RE WP RET minus theta RE WP RET A. because of this, we can write this, and also W bar equal to WE plus, remember that this is antisymmetric bar, antisymmetric bar, antisymmetric bar, and antisymmetric bar. WE equal to RE WP RE transpose times theta A RE dP RE transpose minus theta RE dP RE transpose A. So, and here is another assumption. That is, remember we have first assumption here, small elastic string assumption, and here is our second assumption, is that we assume the rotation is 0. And this can be satisfied if we are dealing with an isotropic material. So with this, we get this W is 0, this W is 0. So what we get? So from this equation, we name them as equation 8. So from the equation 8, we can get D equal to D plus RE dP RE transpose. And this is about the end of our derivation. Here we name this as dP hat. So we can write this additive decomposition. This is the additive decomposition we are looking for, this one. And sometimes we just directly write this as the plus the deformation, the plus the part of the rate of deformation tensor. With this, we have derived from the multiplicative decomposition in terms of f to our rate of deformation additive decomposition. And now let's review that what we did is that two assumptions are very important. First, it's small elastic string. So it's elastic string very small. Second, its rotation equal to 0. So with these two assumptions, what you need to do is just write out the decomposition of L. So basically it's that you have that decomposition of F, you substitute F, you have the decomposition of L in terms of F, and you substitute it, and then you get that solution. I hope this video is helpful for you. So let's have a review. What we did is that, so initially we have this, so we want to derive from here to here. What we do is that by taking advantage of the velocity gradient tensor, we substitute this Fe times Fp equal to F, this decomposition into equation 2 to express the velocity gradient tensor, and we write them out. We can have all this, and further we have F here, so we write this polar decomposition. So by using polar decomposition, we write out the deformation gradient tensor. And once we write this out, we can explicitly show that this is the string, elastic string, and by using this small elastic string assumption, we can ignore this higher order term. And with this higher order term ignored, that we just focus on the rest of the equation. And because this equation is equal to L, so by this decomposition, that's the symmetric and antisymmetric decomposition, we can figure out which part of this is symmetric part and which of this is antisymmetric part. So all of these are just for recognize which part of them is symmetric part and which of them are antisymmetric. And with this, we can write out the symmetric part and antisymmetric part. The last assumption is that we assume the rotation is 0, which is naturally satisfied for isotropic material. And with this, we can get this equation. And this equation is directly the additive decomposition. If you have any questions, please leave a comment, and also comment on what you would like to see in the future. If you enjoyed this video, please click the thumb up and like it. Also share with your colleagues. Alright, with all of this, see you next time. Bye.